Thank you. Welcome, everybody. We are thrilled to be here. Thank you for having us. We are here today to talk about a little bit of about diagnostics in the car, how we shake this up a little bit. I think this is a little bit newer. I'm Thilo. I'm a product owner and software architect in SDV matters, and working at the intersection with open source, basically. And I'm a project lead for OpenSOVD, and and I have with me.
Sorry, I'm Alex. I'm a senior software engineer, also at Mercedes-Benz Tech Innovation. I'm doing the lion's share of my work in the OpenSOVD part, mainly working on the Classic Diagnostics Adapter. What exactly that is, you will learn if you don't know in the next couple of minutes. Then take it away, Thilo.
Yeah, thanks. So let's dig right in. So just a short reminder or 101 on what is SOVD, Service-Oriented Vehicle Diagnostics, actually. So this is basically the newer version, I would say, of vehicle diagnostics interfacing. You probably have heard, if you had some exposure to vehicle diagnostics, about UDS, Unified Diagnostic Services. We will be talking about that a little bit too. But SOVD is basically the newer, or the version that is more fitting into the SDV era. Because it's using more modern technology, right? UDS is basically based on bit manipulation and a very intricate protocol on the vehicle bus, and SOVD is basically HTTP and RESTful interfaces. It uses known standards like HTTPS, OAuth, which we also will see a little bit, and has self-descriptive capabilities, and so it's much more modern. On the left side, you see a little bit of an architecture, or how this is set up in a vehicle, right? You have externally, you have these diagnostic testers that talk SOVD, and some talk still UDS. In the case of SOVD, they talk in the vehicle to something that we will call, or would call, the SOVD server, and which then calls diagnostic functions in the vehicle in applications that expose that functionality. Or if you have UDS-based, so old diagnostic protocol-based ECUs in your car, needs to somehow translate that SOVD request to UDS. And we have that CDA component, Classic Diagnostics Adapter, in the SOVD architecture that does that. We will talk mostly about that because this is what we as Mercedes-Benz are contributing in SOVD, and therefore know most about that. There's, of course, other components that get contributed to or need to be in that software stack, in the SOVD stack, which is also a big topic in the OpenSOVD project. So what is actually that? So the project OpenSOVD is basically the idea that we take the SOVD specification, which is laid out in ISO 17978, which is openly accessible to everyone, and attempts to be an implementation of that, basically, right? And attempts to implement all these software components that are in that SOVD architecture that we just saw. And with that, it tries to foster the standard, because SOVD is a standard which is pretty new. And we try to build some trust in the community and give the standard a chance of adoption in the end. And also, on the other hand, we try to make it better by real-world experience that we learn through our implementation in that project, and try to drive these learnings back to the standards, which we will talk also a little bit later about it. Then we will try to build a bridge between SOVD and the old world of diagnostics. We will talk mostly about that today. And of course, we see this as a building block, as a diagnostic subsystem that will be integrated in Eclipse S-Core. Yeah, so what I now want to show you is an application of OpenSOVD, what we have today in that project, to a real-world thing. So let's roll the video. What you have just seen is an application of what we have in OpenSOVD, mostly the Classic Diagnostics Adapter, to our GLC car. And we just reflashed the light animation of this welcome animation from the Mercedes star to the OpenSOVD logo. And that is done, and you can imagine that car is still built, and this light ECU is still built using UDS. And so what we have to do is we have to bridge the world between good old UDS, which is not to go away, right? That will stay, and this modern world, SOVD, that we want to have going forward, right? And to do that, in the SOVD architecture, there is this building block called Classic Diagnostics Adapter, which receives SOVD requests on one side and translates that into UDS protocol and interaction with UDS-based ECUs in the car. And so we're building that, and while we're building that, there is a couple of things that we keep in mind. One is extensibility, which Alex will talk about in a second. But on the other hand, it's very important that we have the reusability of code also in mind. And we do that here because, yes, if you get from modern clients outside the vehicle SOVD request, that's nice. But there's also a world of UDS-based testers still. Right? Most of us in our garages and after sales have still UDS infrastructure. And maybe you want to provide in your vehicle SOVD infrastructure, but you have an UDS-based client out there, and so you have to have a UDS to SOVD adapter somehow, which is the other way around from the Classic Diagnostics Adapter. And so while we're building the Classic Diagnostics Adapter and can talk already UDS and translate things from one to the other way around shouldn't be so hard if we can make sure that we reuse code, right? And so that's what we aim to do there. Also, there's other points and other areas where we have reusable components, like we have to understand SOVD topology and stuff like that, which is also, and SOV data types that could possibly be reused in a SOVD server component, and even projects beyond OpenSOVD. And with that, I guess I give this over to Alex.
Right, thank you, Thilo. So let's take a look into how the community is actually building this. Although we at Mercedes-Benz are very interested in the Classic Diagnostics Adapter for obvious reasons, otherwise we wouldn't spend time and money to develop that. It's not only Mercedes-Benz who is developing that. We are trying to build a community that is using OpenSOVD. So I've picked three totally random examples that were implemented not only by us, but with the help of our community. So the first thing I want to talk about is a DLT tracing appender. So the OpenSOVD project is heavily building on Rust, and the tracing framework that is part of the Tokyo project is the de facto standard when it comes to tracing in the Rust project. So we wrote a wrapper for the DLT library that is directly integrating into the tracing framework. So in case you don't know, DLT is the de facto automotive standard when it comes to logging. DLT stands actually for Diagnostic Log and Trace. And there's a very commonly known implementation by Covesa that many companies are using. And we wrapped that library, and the reason for wrapping it instead of just re-implementing everything in Rust is because a lot of companies actually are extending the libDLT internally, and we don't want to break that compatibility. So by wrapping it, we provide a way to safely interact with that library, but still maintaining compatibility to the existing workflows and the things that are running actually in the vehicle. Yeah, so much for DLT. One more thing you might think, well, as logging is boring, why are you even talking about that? And you're not the first guys to implement a wrapper around DLT. What's different with the OpenSOVD DLT wrapper? Well, mainly two things. First of all, it's part of OpenSOVD, so it doesn't rot in some side project that is maintained by someone in case they have any free time left. No, it's really supported by OpenSOVD for shipping that as part of OpenSOVD, and that's the second reason you get support for that. In case you find a bug, you have an issue with that, you can open an issue on GitHub, and you will get replies, and we will try to fix your issues. Okay, I think I talked enough about logging. Let's take a look into another example. So, as we already teased in the previous slides, the automotive industry is using ODX to facilitate the ECU descriptions. So in very, very high-level terms, ODX describes which services exist on an ECU and how to talk to them, which services there are, which parameters they have, and, for example, which the service ID is. While ODX is here to stay, or at least for the foreseeable future, if you're not coming from inside the automotive world, it's a complex format. It requires tooling to create or to maintain it. So one of our contributors came up with the idea, why we're not using a format developers are using all the time, like, well, YAML. And so they opened a suggestion, a discussion in our community, and they just started building it. So right now we have a prototype implementation where you can use YAML to describe your ECU. And I showed it later in the demo how it works exactly, so I won't go into further detail here. But that is a very cool approach, especially for prototyping, or if you want to play around with simple ECUs or to create testing. Yeah, so let's skip to the next thing. We are trying to, no, we are not trying. We are making sure that OpenSOVD is compliant to the to the SOVD standard. A great example for that is when we've implemented default endpoint in OpenSOVD. So default endpoint means you can query which data trouble codes an ECU has. We implemented something that was compliant to our existing solution, but that wasn't compliant to the SOVD standard. So one of our contributors during a code review mentioned that, well, hey, look into the standard, there's a compliant way to save that, to implement that. And although that broke our internal compatibility, so we have to implement something that we're getting our backwards compatibility back, we've made that breaking change and implemented something standard compliant. And that's something we are really proud of, that we are focusing on being compliant with standards and making something that is working for everyone and not only something that is working internally at Mercedes-Benz. So what I'm trying to say is that OpenSOVD is trying to be useful for everyone, and the slide title, Open Source Compound Interest. What I mean by that, every contribution we get makes the product more valuable and is further making it usable for another use case. So it can add a new functionality, it can improve standard compatibility, but sometimes even a single suggestion or a single comment can change how core functionality works. And yeah, let's dive into one of these stories. So, the power of community feedback. I already told you that we're usually using ODX and YAML files, but that's not the whole truth. Both of these file formats are text-based and they're complex to parse, they take a lot of storage, so we're actually not using that on the vehicle. We're using a format called MDD, which stands for Marvelous Diagnostic Data. It's a binary format, and the first version of that MDD format was built on a protobuf. So we spend a lot of time into improving the protobuf implementation, so its performance, it achieves our CPU time goals, our memory goals, and the thing with protobuf is that it's maybe not the ideal format to store things like that. So eventually we ran into performance ceiling with that. We had some intermediate layer that made accessing the data in these MDD files a bit easier. So basically it was converting the data in from the protobuf format into something more digestible or something we can query when we run requests. So you can imagine in case SOVD request is received on our RESTful interface, we somehow have to look up what that service means, how to translate that into a UDS service, and how to actually talk to an ECU to that. And if we receive the UDS response back, we have to go all the way back, to take a look into the MDD file again, and translate that back into the SOVD reply. That means every request and every response has to take or has to make lookups in the MDD file. As you can imagine, there are quite a few requests when you're talking SOVD. For example, if you're flashing an ECU, it's not like one request every 5 minutes, but it's request after request after request. So it's very important that the MDD file is performant. So while we had our intermediate layer, eventually we ran into performance ceiling. We had some ideas how we can improve that, but that meant further caching, that also used more memory. We already had some caching in place, for example, for strings. But when we published our benchmark, we got simple feedback from a community member. Hey, have you tried flatbuffers instead of protobuf? The community member had experience with flatbuffers for similar use cases, and while it's obviously not straightforward to replace your whole serialization layer, based on the discussions with our community, we were very confident that this would improve the Classic Diagnostics Adapter substantially. So we took the time, adjusted our application that is converting the ODX files into MDD files to spit out flatbuffers instead. We adjusted our CDA to accept these files. And well, we ran our benchmarks again, and I'll I'll show you the numbers. So I'll give you a second to parse that. As you can see, we got a bit of improvement. So we're using half as less memory. Our CPU time is 76% faster. The peak CPU is 89% faster, and the response time, which means from the SOVD request to the UDS request and the response and back to the HTTP response, was 74% faster. So that's quite substantially by only replacing the serialization format. The reason for these gains is a bit obvious if you take a look into how protobuf or flatbuffers actually work or how they differ. If you're serializing or if you're reading a message in flatbuffers, flatbuffer works by just simple offsets, and if you're accessing a message in protobuf, you have to parse huge chunks of the MDD file and then have to build an object graph in memory that takes a lot of allocations, and flatbuff just doesn't need that. So by removing all that, we got these improvements, and that's something that was built by the power of community and by working together. So all of these things live in OpenSOVD, but if you're an OEM, you have your own implementations, your own needs, your own requirements. So OpenSOVD is only useful for you if you can actually use it. So in OpenSOVD, we've designed interfaces from the get-go so you can actually extend this. So we have a few examples, and I'll show you in the demo in a second how these things actually work together and how they integrate into OpenSOVD. I want to pick two examples here, and first of that is the custom security. So security is very, very OEM specific. Every OEM has its own security, their own requirements, their own way how to fetch a token or how to validate them. So while we do have a very, very basic implementation of that plugin in OpenSOVD, that's something we say if you're BMW or if you're Mercedes, you want to implement that yourself because you want to keep your security plugin and your security infrastructure private and don't want to open source it. And hey, if you want, we won't stop you. And the other thing is, on the bottom right, we also support OEM-specific features. That basically means you can add whatever you want into OpenSOVD without even touching OpenSOVD, without touching the open source part. You can add custom routes, for example. So for our demo, I built a custom security plugin that is using Google's OAuth to authenticate against the CPU. So we're using cloud technology to authenticate against the vehicle. And that plugin was mainly built using agentic AI, and that shows you how simple that's actually, how that actually is. And it's using very little code. I'll show you the thing later, and you wonder, hey, Alex, that isn't little code. That's because I had way too much time and way too much fun by extending that plugin with all the recommendations Google has to actually validate these tokens. And it's almost production grade, but please don't use it without a security review. So the OEM-specific features, what can they be used for? Let's imagine you have such a plugin that is using Google OAuth to authenticate your users against the CDI, and you have a configuration file that is mapping an email address to a role for a user, and you want to reload that configuration file at runtime. Then you add a custom route for OpenSOVD that reloads that route or reloads that configuration file on the fly, so you can change access control at runtime. If you think that's a good idea, I'm not sure if that's really something you want to run in production, but it's great for demonstration. So, let me take a look. Yeah, that's actually all I have prepared for slides. As you know, and you might have noticed, I'm a software engineer by heart. I'm very keen to talk about these things, But I also want to show you how it actually works. So I already said I prepared the Google Earth authentication plugin. You're building, well, I've built an ECU in YAML, but I'll show you how that works and how that is integrated into the CDA. But I'll spare you the rest of that slide. Well, I don't. So that's better. Awesome. Okay, so that is a YAML file for our test ECU. It's a flux compensator, so if you're keen with Back to the Future, you already know what it is, but basically facilitates time travel. So at the beginning, we have some metadata that's boring. We have the ECU name. We have the protocols we support. That ECU only supports UDS and DUIP, IP addresses, and then we have the services. At the moment, that ECU only supports read data by identifier, and we can then define some data identifiers for that ECU. So we have defined a few identifiers. For example, we can read the name of the temporal technician, so we know who did the last temporal displacement. And we can read the last temporal jump date, so we know when the last time travel happened. Unfortunately, setting these things isn't implemented because we couldn't figure out in that short time how to actually implement time travel. So we focused ourselves on actually reading when the last time travel happened. Important to point out here is that that service is restricted to a given audience. So that means the after-sales user cannot access that temporal jump date info because it's a bit of sensitive information, so only a user that has the development role can actually read that. For the temporal technician, while it's maybe PII, we still allow the after-sales people to read that. Maybe keep that in mind. That comes in later when we take a look into the implementation of the plugin. The rest is necessary for the identification that it works with our ECU simulation. Access patterns, we only have public read. That means it doesn't need any special authentication aside the roles we just discussed. And then we can define some data types like the technician name. It's an ASCII string with at most 255 characters. And the temporal jump date is a structure that has a couple of fields. And the rest of that file is boring. It defines DUIP settings, UDS settings, the variance that ECU has. That's basically necessary so we can actually use our ECU simulation to talk to that flux compensator ECU. So, how to actually use that? Our current model is that you integrate OpenSOVD as a library. So you still roll your own main function and integrate everything that is OpenSOVD as a crate, so as a library, in case you're not familiar with Rust. And then the main function is just setting up boilerplate code, parsing arguments, well, you know, the boring stuff. Eventually starts the web server. But that is the interesting part. So that sets up the OAuth plugin and eventually the vehicle routes. But we want to take a look into the Open Authentication plugin. It's loading a configuration file. I've teased it, but also boring. That is the function to actually add the routes. You can see it's pretty simple. We have two routes, one for the OAuth callback and one for the rules. But let's take a quick look into how that plugin actually is implemented. So that is the interface with the CDI. Let's scroll to the end. It's 300 lines of code, a bunch of comments, and the interface is pretty simple. So the trade basically defines two things. We have an authentication plugin that is running with every service call. That is basically checking these audiences we just took a look at. And we have the other plugin part that is doing the authorization. In case of OAuth, that would be fetching the key. So when we run that, or when we convert that file into an actual MDD, we have this file. No. Okay.
Turn presentation off.
It should. Entire screen, stop mirroring. Hey, change. Help, Thilo?
You might want to turn off presentation mode.
I mean, I can kill PowerPoint.
Or that.
We'll find our way back into PowerPoint. Sorry for that. So if you take a look into that little GUI tree, you can't read at all. It doesn't matter. So that is just a little terminal interface that you can use to browse the MDD files. Bit of a teaser, we are actually using that and extending that with an MCP server, so you can eventually ask your AI about your MDD files. For example, a use case for that is which services are used for authentication, and the AI then spits out all the relevant services. So that's currently a personal project of mine, but we will make that part of OpenSOVD eventually. So I have to hurry up a little bit. I have the CDA running in the background. Not interesting how to start it. I'm just running a shell script to start it. It's all documented, so no worries in case you want to try that out. You will find your way into that. So that is the actual REST interface. So we see our flux compensator ECU is online. When we now try to read session, we're not allowed. We don't have any token. And then I wrote a little script that is authenticating us. It takes us into Google. We can choose an account. I'll need my phone to verify that's actually me. And then we can continue. And as soon as we have the authorization code, we can paste it into our little shell script, and it's doing some things. So basically, it's calling the callback endpoint. We saw how it's registered. It's passing the authentication code. Then the CDA is calling back to Google and exchanging that authentication code with a token. And then the script is also trying to lock the ECU. And then if we copy that access token into our clipboard, we can add that here. And you can see I'm very well prepared. Oh, I messed that up. So give me 1 second. Because the URL is actually named like the service, so we can copy it from our YAML file, so it doesn't matter if you mess up your prepared demo. And you can see the last temporal technician was Dr. Emmett Brown. The other service is the read temporal technician, the last temporal dump date, sorry. And we can see here, our user is not allowed because it doesn't have the development rights. And if we take a look into our configuration file, if I happen to find it, if we take a look into our let's just search for the email. Then we see that my user is only an after-sales user, so I am not a developer, as it seems, and I can't access the rule. And we could change that to development, then reload the configuration, and then we would be able to call that service. But as I don't want to steal the last 10 minutes from Thilo, I'm gonna spare that, and let's continue with
slides,
the boring stuff.
Yeah. Oops, the clicker somewhere.
I have the clicker here, and I'm selecting the correct slides for you.
Wonderful.
So, thank you, Thilo. Take it away.
So, did you notice the flux compensator still uses UDS? So we have to do something there. Yes. So, I want to just spend a few minutes on talking about what we, besides the tech do or try to do in OpenSOVD, aim to do there, is, like, as I already mentioned, take what we learn while we implement all these things and work with the flux compensator, put that into the standardization of SOVD, right? We have a first version of SOVD, ISO 17978, and that is going to evolve over time, right? And what we want to do there is put things that we discovered along the way and into the standard, of course, running it through the committees and putting into standard Ds and, make it an ISO wording, kind of ISO standard wording. But things like the SOVD server topology is largely discussed, like how do we order entities, what is the tree there, right? Things like things that we learn from the CDA that I have listed a couple of them here on the slide. These are all stuff that you just know, can know when you were actually doing it, right? And so one of the great things of OpenSOVD is that we do these things and learn these points and can improve the standard and make it a better standard and evolve that over time. A couple words on why this works exceptionally well in open source is because we have a community and a couple of people coming together. Just like Alex said, we got feedback on our protobuf implementation. It's like, hey, did you consider flatbuffers somehow? And that only works because we are getting together with other people and have our own echo chamber, right? And learn from them and improve together. So more brains on the project means a better project and better implementation at the end, right? And in the end, it's trustful collaboration there. We don't need to take a lead on just everything because people are joining and organically choose their topics and things that their hearts are attached to and enrich the project there. And through that, we gain innovation, learnings, standard evolution, all these things. And with that, I guess I just can call to action. Try it out. Test the flux compensator and contribute on GitHub. We have like a QR code up there. You will land on our GitHub organization. You can join our meetings. We have a couple of them every week. Architecture board is probably the most central one where you can just drop in and discuss overarching topics or your entry to the project. And or dive in the code, leave comments, do reviews, whatever, right? We will be around at the conference. Talk to us if you want to engage. Drop us a mail, whatever, right? follow the QR code. And with that, I want to end and say we are in this together, we as an automotive industry, so we have the chance to build exceptionally cool code in our open source community, and through that evolve the standard, and let's do this together. Thank you, everyone.
Thank you, Thilo. Thank you, Alex. Very, very, very cool stuff that you guys are doing. Can I get one of those Mercedes? Any questions from the audience before we break for coffee?
In case I want to add the flux compensator into my car to try things out, do you have the demo somewhere visible, or another demo or tutorial to get started with OpenSOVD?
So that YAML that is not open source yet, but the main reason for that is just because I didn't want to spoil the OCX talk. We will open source that as well. But the YAML file is actually based on the CDA's own tests, so we do have the ECU already defined via ODX tools, which is also another open source project. So you can take a look into the Classic Diagnostics Adapter. There you find a bunch of Python files that generate basically the same ECU, just based on the ODX tools, because they are more mature compared to the YAML implementation.
And you mentioned that the Classic Diagnostics Adapter is some kind related to the S-Core. So it's part of it or so, because you mentioned on the slide, it says Classic Diagnostics Adapter S-Core.
Yeah, we try to, so we want, well, where is it?
The thing that is one.
That one, right? It's before the video, so there you go. Yeah, so as an overview to OpenSOVD said, we want to be integrated in Eclipse S-Core, which is currently not the case. We are working towards that. I believe that in the near future you will see more activity around that. We try to organize talks between the two communities. There are somewhat overlapping, but not totally, right? So we try to bring S-Core and OpenSOVD folks together in the coming weeks and talk through this, how this can be done and what needs to be done to achieve that.
Thanks.
And by the way, this is not about only the CDA. So to be an actual diagnostic subsystem in a middleware, automotive middleware, we have to have more stuff like that you see on that slide, like all these nice boxes there, right? Like SOVD server and like libraries that you can load into your applications to talk to these components, like to report faults or to execute diagnostic routines or whatever, right? That has all to be done, which we call the fault lib and the fault manager and stuff. All these things have to go into the diagnostic subsystem of a middleware, and so we have to increase a little bit on our momentum on these components, I guess, but eventually we will get there.